Hi everyone, I'm Ruofan from Institute of Science Tokyo, and today I'm super excited to present PM muscle, improving piano skill acquisition by cost-effectively estimating and visualizing activities of miniature hand muscles. This work was done with my awesome collaborators, Ichen, Takanori, Chenche, and Erwin, as well as my amazing supervisors, Shinichi Furuya and Hideki Koike. Skillful human movement encompasses interactions between the muscular and skeletal systems. Quantitative assessment of muscles could facilitate various applications, including rehabilitation, fatigue prevention, and enhancement of skill acquisition. But contemporary muscle measurement either requires electromyography sensors and lab environments, or confines to gross motors involving large muscles. For dexterous movements like piano performance, neither of which is really practical for pianists. So instead, in this research, we proposed PM muscle to explore the efficacy of using readily accessible data, such as videos and keystroke motions, to infer muscles EMG, and subsequently compare pianist hand muscle activation with the reference to enhance force control in piano training. So there's been a lot of work done in evaluating the muscle activities with external instruments. For example, sensor-based systems like Delsys and Muscle Rehab use prohibitive sensors in controlled lab settings to record muscle engagement. However, these systems require high cost or high computational demands and are inaccessible for most consumers. On the other hand, data-driven and machine learning-based methods like OpenCAP demonstrate high accuracy when the input data falls within the distribution of the training set, which means it just focuses on gross motor dynamic prediction. Thus, overall, cost-effective methods for estimating miniature muscles remain largely unexplored. To address these issues, we proposed a workflow to estimate miniature muscles activities from human-centric data and more accurately when combined with tool-centric data. And we also visualized inferred muscles and conducted user study regarding the estimation accuracy and piano training effectiveness. So first, we invited professional pianists to collect a multimodal dataset. 6 muscles of a single hand were specified, and an RGB camera was fixed to the top middle of the piano to record the videos. As for keystroke motions, we utilized an optical sensing system from previous work. After pre-processing all collected data, we compiled 8 million frames of keystroke and EMG, along with 480,000 frames of videos. Here's a detailed look at our network architecture. To avoid potential distortions in direct estimations, we trained 2 VQVE at the first stage. Rather than directly downsampling the EMG, we constructed a discrete codebook for EMG representation to reduce EMG temporal complexity. Meanwhile, a codebook for pulse to compress it in spatial dimension. In the second stage, a cross-attention-based transformer, EMG former, was introduced to predict EMG from keystroke and video inputs. We encoded the keystroke with the TCN and the pulse with the pre-trained pulse encoder. During training, we froze the parameters from the first stage and optimized the loss by minimizing the EMG embedding loss. Ablation studies were conducted to validate model estimation performance. Interestingly, we found the experiment using only video demonstrated notable accuracy, while more modal inputs like keystroke motions can further improve accuracy. Here's an example focusing on 4D eye muscle. The blue line represents the ground truth EMG, while the orange displays our estimated values. And we also listed more performance results here. The top figure shows the ground truth, while the bottom presents our model's predictions. Based on the network, PianMuscle visualized the inferred muscle activity after temporarily aligning the users with the reference using KTCC. Well, here, KTCC refers to a custom network to achieve accurate synchronization, specifically tailored for piano performances. Then the aligned videos, synchronized hands, and discrepancy prompt on the timeline were displayed to show the muscle difference. And click the flip model bottom here to see the palmar side. With PianMuscle, we conducted a user study with 5 highly skilled pianists, without and with muscle activity visualization. Specifically, they experienced 2 comparative conditions, each session for 30 minutes, and their pre-study and post-study performances were recorded for quantitative analysis. A comprehensive evaluation of the system can be found in the paper, but here let me just go over a couple of highlights. So here, higher MAI represents better force control, and overall, pianists show a greater improvement in muscle accuracy under PianMuscle. Higher KAI and KCI represent more accurate and closer keystrokes to the reference, and our system achieves better results too. As for questionnaires, PianMuscle obtains higher scores in all dimensions from UE key results. Regarding helpfulness, intuitiveness, and operability, PianMuscle is better than only videos. Also based on participants' rating for the visualized muscle accuracy, it's similarly accurate from their previous experience. In interviews, all pianists preferred PianMuscle because piano muscle information is intuitive and objective. They acknowledge that estimating and visualizing muscle activities is an effective method to facilitate force control training. From previous results, we can confirm it's feasible to cost-effectively estimate miniature muscle activations from readily accessible data. And furthermore, this workflow can be adapted for other skills, especially for dexterous skills. We also conclude that PianMuscle can be a supplement tool for conventional piano training, because it can provide objective muscle information for reference instead of absolute correctness. And it can also address some video limitations, such as hand occlusion and audio distortion. To summarize, we present PianMuscle, a design workflow that democratizes muscular activity monitoring by cost-effective estimation from readily accessible data, and visualization to enhance acquisition of various dexterous skills that rely on small muscles. Please refer to our paper for more details and results. And thanks, and see you around the conference.